Hello, my name is Reza and welcome to my presentation. Today I'm going to present our work, Temporal Memory Safety via Robust Points to Authentication. As you know, temporal memory corruptions are pretty common in unsafe programming languages such as C and C++. So they are attractive targets for the attacker. So far, many solutions have been proposed. However, these state-of-the-art approaches rely on a huge amount of metadata to track the objects, pointers, and their lifetime in the memory, which leads to high memory overhead. Also, the metadata is left unprotected. Technically, these approaches assume that spatial safety is in place, or other techniques such as bound checkers can protect the metadata. In our work, we are going to detect temporal memory corruptions in the heap during the runtime. However, we are going to answer some important research questions, such as, can we design a system with low memory overhead and reasonable runtime overhead? And also, can we guarantee the integrity of metadata without relying on other approaches? To do so, we propose PTAuth. Our system checks upon each pointer dereference, whether the pointer is pointing to the original or intended object, and whether the metadata and the relationship of the pointers and also the objects are genuine. But how we can achieve these goals? We use PAC. PAC stands for Pointer Authentication Code. Technically, PAC is an extension of ARM architecture, and it can provide value integrity for the pointers. It has already been used in iPhones to provide control flow integrity. The input of PAC is just a pointer and a context, and the output is a signature. This signature is stored in unused bits of a pointer, and it is applicable in 64-bit system. As I mentioned, PAC has already been used for providing CFI for data pointers or code pointers, but in this paper, we're going to use PAC for data pointers and provide temporal safety. We divide memory into two sections, pointers and objects. For the objects, we generate a 64-bit random ID, and it's located exactly before the object in memory. Technically, the metadata is in line. For the pointer, we use the base pointer of the object and also the ID of the object as the input of PAC-IA instruction. Then we generate a signature based on that. This signature is stored in unused bits of the pointer. Therefore, by this technique, we are able to make a connection between the pointer and the object. This figure shows big picture of our system. Technically, during the compile time, we instrument the LLVM bit codes. At allocation sites such as malloc, we generate signatures for the pointers. At dereferencing sites such as load and store, we authenticate the pointers. And in deallocation sites such as free, we invalidate the ID of the objects. Therefore, we can detect dangling pointers. As you can see, in runtime library, we use PAC-IA instructions for generating AC, and we use auth-IA instruction for authenticating the pointers. If we cannot authenticate the pointers, it means that the pointer is a dangling pointer, or a spatial corruption has corrupted the ID of the object. That's why the pointer cannot be authenticated. In our design, we assume that the pointer always points to the beginning of the object and ID is located before that. Technically, ID is in line. However, this assumption is not always true. There are some cases that the pointer is pointing to the middle of the object. For example, in the case of pointer arithmetic. In order to find the ID of the object, we propose a solution which is called backward search. Technically, in this method, we go upward until finding an ID that can authenticate this pointer. We do some alignment for the objects to find the ID of the objects faster. For example, we align the objects to 16 bytes. In the next round, we do some optimization to remove some redundant checks. Technically, this optimization works best for single-threaded applications. There are some cases that the pointer is passed to a function, and then this pointer is not passed to any other functions, and also it's not passed to free function. Therefore, the checks are redundant. For example, in this case, the reg pointer is passed to quantum gate2 function, and then there are a couple of authentication. However, all of them are redundant until we reach to quantum add hash function. At this point, the pointer is passed to this function, and we cannot track it because our analysis is intra-procedural analysis, and we can only check inside of the functions. Therefore, we remove these checks, and after passing the pointer to quantum add hash, we enable checkings again. At the time of doing this research, there was not any hardware that supported pack instructions. Therefore, we had to test our idea on top of FVP simulator. However, the simulator was not robust enough to run our benchmarks. After a while, Apple introduced new iPhone that supported pack instructions, but we were not able to run our benchmark on top of iPhone without jailbreaking. So we chose another option. So we decided to go with software implementation of pack instruction to test our idea and get an estimation of our design. So we implemented PackIA in software. It's not exactly following the spec of pack instructions, but we could get an estimation for our work. We used Raspberry Pi to run our benchmarks. To measuring the overhead, we selected 9 benchmarks from SPEC 2006. So all of these related work have been used, these 9 benchmarks. So we could do some comparison between our work and other works. As you can see, the runtime overhead of our system is a bit higher than other systems. But because we use software implementation, hopefully these numbers are lower in real hardware and with real pack instruction. The geometric mean overhead of our system is 26%. In another experiment, we intended to show the practicality of backward search. Therefore, we measured the overhead of backward search for each benchmark separately. As you can see, the numbers are almost low, so it shows that the backward search is practical. The memory overhead of our system depends on the number of objects in the memory, because for each object, we add extra ID, and also sometimes we need to do some alignment. But in compared to other works, we have low memory overhead because we use unused bits of the pointers to store the metadata for the pointers. Therefore, we do not have that much overhead. The geometric mean overhead of our system is almost 2%. In this work, we presented a resilient points to authentication technique for detecting temporal memory corruption. Technically, we repurposed PAC on ARM to detect temporal memory corruption. Also, our system is able to provide metadata integrity for objects and pointers without relying on bound checkers or without any assumptions such as spatial safety. Thanks for attending my talk. I would be happy to take any questions.